First, what is the definition of multivariate random variables? So we know what's the definition for the univariate. So if X is a univariate, this essentially is a mapping from the sample space to the real line. Now we can extend this definition to bivariate random vector. Given a random experiment with a sample space C, consider two random variables, x1, x2, which assign to each element C one and only one order pair of numbers. So now I have a random vector x1, x2. So it is also a mapping from C to R2. So it's two-dimensional space. So you give me a C, I will give you two numbers, little x1, little x2. These little x1, little x2, they are inside the two-dimensional space. So this mapping make x1, x2 a bivariate random vector. Now the space of x1, x2, it contains all possible values for this random vector. This definition can be extended to a random vector with any dimension. For example, you can define an n-dimensional random vector. So this will be a mapping from a sample space to an n-dimensional Euclidean space. So that's how you define a random vector. There are two most well-known multivariate random variables. One is discrete, another one is continuous. So for discrete multivariate random variables, it is called a multinomial distribution. Now we talk about binomial distribution last time. So binomial distribution, if you perform an experiment, each time you will have two options, either head or tail. You perform this experiment n times, you count how many heads you observe. For multinomial distribution, now for each experiment, you have k options. So this is k. For example, you toss a die, you have 6 options. So the number can be 1 to 6. Now you have k options. You perform this experiment n times. Now you count how many first situation, x1, how many case situation, xk. Now you put the counts together. This follows a multinomial distribution. Now for each situation, you have success probability, p1 to pk. So this will give you the multinomial distribution. So they are discrete random variables. Now, if they are discrete random variables, we can write down the joint PMF. So for example, probability x1 equal to little x1, xk equal to little xk. So this is equal to n factorial x1 factorial xk factorial, p1 x1, p2 x2, pk xk. But the total sum, of course, the sum xi I from 1 to k should be n. The success probability pi I from 1 to k should equal to 1. So this is the PMF for multinomial distribution. You can integrate out the individual one. Actually, for marginal distribution, for each xi, it's a binomial distribution with npi. So these are the properties of multinomial distribution. Another important distribution is called a multivariate normal distribution. So this is a continuous random variable. So this x, for example, is an n-dimensional random vector. It follows a multivariate normal. So we have a mean vector. We have the covariance matrix. So this mean vector is mu1 to mu(n). So this covariance matrix is a n by n matrix. It's a symmetric matrix. The element, ij's element, in fact, it is a covariance between xi and xj. So it's called a covariance matrix. The joint PDF is complicated. So the joint PDF x1 to xn, it can be written as 1 over 2 pi n over 2. This is a matrix determinant. Take square root. So it's e to the negative half. This x minus mu. This is a vector. Transpose sigma inverse x minus mu. X can be anything. So this is a joint PDF. So this is a determinant. This is inverse. That's a multivariate normal distribution. Is an important multivariate distribution. Now let's move to expectation of the random vector. That's straightforward. The concept of expectation extends in a straightforward manner. For example, I have x1 and x2 be a random vector, bivariate. Let y be a function of x1 and x2. So y, for example, you can calculate what is the expected value of y, where y is x1 plus x2, or x1 over x2. So this is function g. So how to evaluate the expected value of y using the distribution, joint distribution of x1, x2. So if x1, x2 is of continuous type, the expected value of y can be written as this form. So this is the joint PDF of x1, x2. This g is this transformation. Similarly, if x1, x2, they are discrete random variables, you can calculate the expected value of y as this form. You have double sum. This guy is the joint PMF. So this is how we calculate the expected value of y. The most important property for expectation we talked about last time. Expectation is a linear function. So that means every time you see a constant, you can move the constant out of the expectation. Let xy be a random vector. Y1 is a g1, x1, x2. y2 is g2, x1, x2. So these y1, y2, they are random variables. Now I would like to calculate the expected value k1, y1 plus k2, y2. So k1, k2, they are constants. We know expectation is a linear function, so we can move k1, k2 outside of the expectation. We also talk about the expectation is not a nonlinear function. So definitely expected value of g x1, x2, this is not equal to g expected value x1, x2. That's not true. Note that expected value of any function gx2 of x2 can be found in two ways. For example, this is only function of x2. Now we can use the knowledge of last lecture. Expected value gx2, we can use the marginal distribution of x2 to evaluate this expectation. Similarly, for today, I can use the joint distribution. This is joint distribution of x1, x2. In fact, they're exactly the same. You can do dx1 first. You can get the from the joint. You can get the marginal. So these two equations exactly same. For a random vector, how to define the MGF? Suppose I have a bivariate random vector, the x1, x2. Now, how to define the MGF? For example, for one-dimensional case, if x is one-dimensional case, the MGF is e to the tx. That's how we define the MGF. Now, for two-dimensional case, the MGF is a function of t1 and t2. So it's the expected value t1 x1 plus t2 x2. If you write this formula as a matrix or vector form, so for example, if you can define t is t1, t2, so this is a column vector, t1, t2. Now the MGF can be written as this form. So this is t1, t2 times x1, x2. So this formula is very similar to one-dimensional case. If you let T2 be 0, you will get the MGF for x1. If you let T1 be 0, you will get the MGF for x2.